Hello and welcome to the calculator guide video on solving application of forces problems with the equation app on a Casio fx-CG50. We've got two questions in this video. Question 1, we have a 6 kilogram mass lying on a smooth plane, so no friction, that is inclined at 30 degrees to the horizontal. It is attached to a 4 kilogram mass that hangs freely from a light inextensible string that passes over a smooth pulley. The system is released from rest with the string taut. Work out the acceleration of the system and the tension in the string when the system is released. And we're going to use the fx-CG50 once we've set up some equations to find both the tension and the acceleration simultaneously. Now, one thing to just note is when I wrote this question, I forgot to assign which mass was which letter. We've got P and Q on the diagram here. P is the 6 kilogram mass and Q is the 4 kilogram mass. So with that in mind, we can start putting some forces on the diagram. Let's see what's going on. So we're going to start off with the weight of these particles. We have the 6 kilogram mass, that's going to weigh 6g, and we'll take g as being 9.8 meters per second squared in this question. And q is going to be 4g, the force on there. We're going to put the tension in the string. Now we have a light inextensible string passing over a smooth pulley, so that tension is going to be the same throughout. So we're just going to label both of these T. We also need to split the weight of 6g as it's on the slope there into parallel and perpendicular components. We've got 30 degrees as the angle here. The perpendicular component, we've got 6g cosine 30, and the parallel component, we've got 6g sine 30, heading in the opposite direction of the tension of the string. One thing just to point out here is there should be the reaction force going perpendicular to the slope at P, but it's not going to be needed in our calculations, and for the sake of just fitting the diagram in and the room on the page, I've not labelled that in this case, as long as you're aware that that exists. So now we've got all the forces we're going to need to form our equations. What we're going to do is to use F equals ma to form two equations, one at P and one at Q, and then we're going to get the CG50 to help us solve those. So let's write an equation for what's going on at P. What forces do we have involved? Well, the motion of the system when it's released is that Q will go down and P will be drawn forwards towards the pulley. So if we take that direction as being positive, then the tension will be positive. So we'll have T, and then working against that, we'll have the parallel component of the weight of P, which is 6g sine 30. They are all the forces that are acting parallel to the slope. They will equal mass times acceleration, so a mass of 6 times a, which we need to find. Now, in order to get this ready for the calculator, we're going to prepare it by having all the terms which have unknowns in them on one side, then the known values on the other. So in this case, we don't know a and we don't know t. They're both unknowns. We're going to solve them simultaneously. Let's have them on the same side of the equals, and then minus 6g, g we know is 9.8 sine 30, on the other side. So if we rewrite this as 6a minus t equals minus 6g sine 30. So essentially all I've done here is taken the t over to the other side so that we've got the two unknowns on one side. And that's going to be the first equation that we're going to input into our calculator. We're going to solve these simultaneously, so we do need a second one. So let's form an equation at Q. So at Q, the direction of movement will be down. So let's take the direction as being positive. So 4g will be positive. In the opposite direction, we have the tension. So 4g minus t equals ma, which is 4a for Q. And once again, we're just going to rearrange this so that the two unknowns are on the same side. 4a plus t equals 4g. Right, now we have our two simultaneous equations. We're going to turn to the calculator and we want to go down to A, which is equation, and then F1 for simultaneous, and we have two unknowns, F1. It's worth noting here that the A that is here is the coefficient in front of our first unknown. Our first unknown x, that's going to be A for acceleration. So just be careful there. It's x that's going to represent our acceleration in this case. Y is the second unknown, that's going to represent the tension. A, B and C in this case are going to be constants rather than variables, or the coefficients in front of are unknown variables. The second thing to note is we're also going to have to ensure we are in the correct angle unit, because there is sine involved in one of our equations, and the angle unit in the question is degrees. So currently I'm in radians by default, so I just need to change that first. Shift setup and down to angle unit F1 for degrees. Let's double check that's in degrees. So now we can put that in. So first of all, we have 6 lots of acceleration, 6a minus tension, minus 1 lot of tension, minus 1. And then we can input our calculation. The calculation can actually be done within the equation solver here. So it's -6 times 9.8, that's times g times sine 30. Execute, and we've got -29.4. Let's work that out for us. The equation at Q for our second equation here, so that's 4a plus 1t, so plus 1, and then it's 4 times 9.8, 4 times g as our c there. So double check we've got everything in there and press execute. And here we have our 2 answers. Remember that x represents the acceleration here, so the acceleration is 0.98 meters per second squared, and y represents t, which is the tension, that's 35.28 newtons. Just as an additional bit of information here, if you want these in terms of g, you can either take g out of the equations when you write them into the calculator and then multiply it back in when you have your answers, or you can simply divide the answers that you've got here from the calculator by 9.8 to get your answer in terms of g. So in these cases it would be the acceleration would be 1/10 of g and the tension would be 18g over 5. So that's another option if you want it in terms of g. Moving on to the second question, a little bit more complex here, because this involves friction, although some of you may notice that I have used the same diagram here to save time, but there's going to be different forces we're going to apply to this. So let's just have a quick read through. Particle P of mass 4 kilograms rests on a rough plane inclined at 30 degrees to the horizontal. The coefficient of friction between P and the plane is 0.21. A light inextensible string attached to P lies on the line of greatest slope of the plane and passes over a smooth fixed pulley at the top of the plane. So we know that the tension is going to be the same throughout the system from that line there. Particle Q of mass 5.5 kilograms hangs vertically from the other end of the string. Particle P is initially 1.9 meters from the pulley, and particle Q is initially 1 meter above the ground. The system is released from rest with the string taut, and we need to use g as 9.8 meters per second squared. Part A, once again, very similar to the first question we did there, find the acceleration of the system and the tension in the string. Part B, given that Q hits the ground with a speed of 2.5 meters per second, determine whether particle P will reach the pulley. Okay, so a lot of information there. We're not going to use it all at once, and that's why it's helpful to put the forces onto the diagram to see what's going on so we can make more sense of the information. So let's start off with the weight of the particles. This time we definitely know that P is 4 kilograms, so the weight is 4g. The weight of Q is 5.5g, and the tension in the string is the same throughout, so we'll label that as T. Once again, we're on a slope, so we're going to split the weight of P into perpendicular and parallel components. So we have 4g cosine 30 running perpendicular, and 4g sine 30 is the parallel component. We also have friction acting here in this system, which runs parallel to the slope against the direction of motion, which will be P travelling towards the pulley, so we're working in the opposite direction. That's mu r, so mu times the reaction force. So this time it's definitely important to get the reaction force in here. So the reaction force of the slope there, r, and I think we've got all the forces that we need here now. Similar sort of situation, except there's going to be a little bit more information than the first question. We're going to use F equals ma once more. Let's form an equation at P. So the direction of movement will be towards the pulley, so we'll make that positive. So we'll say that T is positive here, and then what's working against it? Well, the friction force, which is minus mu r, and then the parallel component of the weight, which is minus 4g sine 30, and that will equal, and then we've got ma, so that's 4a. Let's just take a moment now just to work out what 𝜇 will be in figures. We know that 𝜇 is 0.21, that's given to us in the question, and R will be, well, in this case, the only force which is working opposite R in the perpendicular direction there is the perpendicular component of the weight of P, 4G cosine 30. So the reaction force there must equal 4G cosine 30. So now we can fill in 𝜇r. Let's just write out what we've got. I'm just going to use brackets, parentheses here just to separate it out. T minus 0.21 times 4G cosine 30, still minus the parallel component of the weight, minus 4G sine 30 equals 4A. And then lastly, I'm going to rearrange it so that the two unknowns are on the same side. So 4A minus T minus the tension equals, well, the friction force and the parallel component of weight there, and they'll both be negative because they're heading in the opposite direction. So I'm just going to outline that. That's going to be going into our calculator. Again, don't worry too much about all the figures there. The calculator is going to do the calculation for us as we did with question 1. So let's form our second equation. That's at Q. We know that the positive direction will be down, so that's 5.5G minus the tension in the opposite direction equals MA, so that's 5.5A. Rearrange for the two unknowns on the same side, 5.5A plus T equals 5.5G. And we'll just highlight that. And so then we're returning to the calculator now. Just going to press F1 to repeat here. You can press exit if you prefer. We've still got the figures in from question 1 here, but I'm just going to overwrite these. So we've got 4A minus 1 lot of T, and then careful here, our last entry is going to be all those figures that we had on the right hand side of the equation for P. So that's minus 0.21 times 4 times G, which is 9.8 times cosine 30, and then minus 4 times 9.8 times sine 30. I'm going to get the calculator to work all those out, press execute, minus 26.72 and so on there. And then the second equation, the equation at Q, we've got 5.5A plus 1T equals 5.5 times 9.8. So we've got 53.9. All the information is there correct, so we press execute and we've got both our acceleration and our tension here at the same time. So we've got X, which is acceleration 2.86 meters per second squared, and the tension is 38.169 newtons. So we're going to have a look at part B now, and I'm just going to erase the working space here, so we've got a little bit more space to write the working out for part B. Given that Q hits the ground with a speed of 2.5 meters per second, determine whether particle P will reach the pulley. Okay, so let's just work out what's going on with P. When the system is first released from rest, what happens is that the taut string pulls P up towards the pulley. Well, how far does it travel until the string is no longer taut? Well, it will travel the same distance that Q travels when it falls down to the ground. And as soon as Q hits the ground, then the string is no longer taut. Well, how far is that? Well, from the question, it says particle Q is initially 1 meter above the ground, which means particle Q can travel 1 meter before it hits the ground and the string no longer is taut. So therefore, particle P will be pulled 1 meter until that occurs. And then what's going to happen is the string is no longer taut and the force from the tension will no longer be there. But at that particular point, P will still be traveling. Remaining forces that are acting upon it, which are the friction force and the parallel component of the weight, cause it to come to a stop. And what we want to try and find out is, does it come to a stop before it hits the pulley, or does it come to a stop after, or i.e. does it hit the pulley before that happens? So what we want to try and find out is, does it come to a stop before the distance equals 1.9 meters, bearing in mind it's already travelled 1 meter, or would it go on further than 1.9 meters, in which case it would hit the pulley? So what we've got to work out is this extra distance that's travelled while P is slowing down to a stopping point. We're We're going to label that distance x. So let's just take a moment just to form an equation for what happens once the tension is gone. So let's use F equals ma again, so that we know that the forces acting are now just the friction force acting in the opposite direction of motion and the parallel component of the weight, and that equals 4a. That's a revised equation for P. Now we're going to use the solver on the fx-CG50 in just a moment to help us out with this, to work out what the new acceleration is. We are expecting that new acceleration to be negative because we're expecting it to be slowing down. But what I'm going to do is this force that we've got, this combination of the friction force and the parallel component of the weight, well, that is C from what we have here in equation 1 in the calculator. That is what we put in, was on the right hand side of our equation in part 1. So for convenience, what I'm going to do is to copy this out. So if I go to C and press F4 for edit, and then I'm going to press shift and clip, and then I'm going to navigate right and highlight that, and then F1 to copy line. So I've now copied that, and so then if we exit out of this and move to, we're still in the equation app on the fx-CG50, we're going to press F3 for the solver. We're going to set up the equation that we've just formed here. So we know that's on the left hand side is what we've just copied to the clipboard there. So if we press shift and 9 to paste, we've now got that right hand side. And of course, feel free to rewrite that completely if you're not sure, if you're not confident to use that, but it is a way of saving a little bit of time and using those same figures. And then we've got an equals, so that's shift and then the point here, so that will give us an equals, and then 4a, so 4 and then alpha a. It'll have to be a capital A, but that's okay. Press execute and then execute to confirm we want to solve for a, and here we have our new acceleration, which is minus 6.68. We knew it was going to be negative because P is going to be decelerating at that point. Okay, so we've got our new acceleration. Let's work how far it travels then under this circumstances. So we're looking for x, so let's just list SUVAT, S-U-V-A-T. The distance is what we're interested in, so that's going to be labelled as x. U, that is the velocity that P would start off at. Well, this is after the string has become loose. So at that precise point, it will be travelling at the same speed as Q was when it hit the ground, because previously the tension was the same throughout and we were looking at the velocity of the system. So the initial starting velocity of P after it's travelled that 1 metre will be 2.5 metres per second. What are we looking for? We're looking for when P comes to a stop. So V is going to be 0, so when the speed is 0, and A, we've just found that out, is now minus 6.6822 meters per second squared. Time is not going to be applicable for this one. So what equation of motion are we going to be using for this? We're going to be using v squared equals u squared plus 2as. And once again, we're going to use the solver on the calculator to help us out with this one. So if we go to F2 and then F1 to delete that equation, now we've got a. And let's just take a moment to type in this equation, v squared equals u squared plus 2as. Now I'm going to use the letters here because we can then assign values to them. You are free, if you wish, to use the values that we've already found if you find that quicker. That's absolutely okay. I'm going to show you how you can do it with the values here. So once we've got the equation in, press execute. We've got all of them potentially there that we can either substitute a value or solve for. Now notice how the a is already in there from when we solved it just. We've already got the acceleration stored from the previous calculation that we did there. So we just need to fill in what else we need. So we know v is already going to be 0 and u is going to be 2.5, and then down to s, and we want to actually solve this. So F6 to solve. And here we have our distance, 0.46765 to 4 decimal places. So that is how far it travels after the string becomes loose. So it's travelled 1 metre when it was in the system, and then an extra 0.46765 metres once it was free under its own motion there, and then that's a total of 1.46765 765 meters. What we know is that that is less than 1.9, which was the distance from P's starting point to the pulley. So what we know is that it will come to a stop before it reaches the pulley. So no, P does not reach the pulley, to finally answer the question there. So there we go, how we can use the equation app on the fx-CG50 to help us with some application of forces problems. These are often quite lengthy questions, as you can see, and it's well worth setting up all your information first before you then use the calculator. The calculator then makes it a lot easier to do some of these calculations and store the figures, so you don't have to keep writing them out over and over again. Don't forget to like and also subscribe for future videos, but that's it for this video. Thank you very much for watching, and I will see you next time on the Calculator Guide.